Picture this. It's 1905. A young patent clerk in Switzerland publishes a paper that's about to completely turn our understanding of reality on its head. And no, it wasn't about relativity, not yet anyway. It was about something we see every single day, light. And his idea, well, it would give birth to the strangest and most successful theory in all of science.
So if you looked at physics at the turn of the 20th century, you'd think, wow, we've pretty much got this figured out. On the surface, everything looks solid, almost finished. But that was just the surface. Underneath, there were these deep, unsettling problems hiding, fundamental cracks that threatened to sink the entire ship of what we called classical science.
Okay, so let's dive into this. What exactly was the problem? Well, it all boiled down to this massive conflict, a deep crack running right through the heart of physics, splitting it into two totally incompatible ways of seeing the world.
And this conflict was huge. On one hand, you've got the theory of matter. Everything physical, chairs, planets, you and me, was understood to be discrete, made of tiny, distinct parts called atoms. It's like a staircase, right? You can be on this step or the next step, but you can't be anywhere in between. But then you had the theory of light, and light was seen as the total opposite, a continuous wave, a smooth, spreading field, kind of like a ramp where you can be at any point along the slope.
And here's the thing, you just can't have it both ways. How can the universe be built on two completely opposite rules? A world that is somehow both a staircase and a ramp at the exact same time. This wasn't just some small disagreement among scientists. It was a fundamental contradiction, right at the core of what we thought reality was.
And, this wasn't just some abstract philosophical debate. It was causing real problems in real experiments. The first major clue that the wave theory of light was in serious, serious trouble came from something called the black body puzzle.
So what is black body radiation? It sounds complicated, but it's really just a technical term for the glow that any hot object gives off. Think of a metal poker in a fire. It glows red, then orange, then white hot. That's it. But here was the problem. When physicists used their trusted wave theory to predict the colors a hot object should emit, the theory just failed. Completely.
And when I say it failed, I mean it failed spectacularly. Get this. The old wave theory predicted that a hot object should just keep pumping out more and more and more energy, an infinite amount of energy in the high frequencies, like ultraviolet light. This was so wrong, so obviously absurd that it even got a famous nickname, the ultraviolet catastrophe. Clearly, something was deeply, deeply wrong.
And this is where Albert Einstein enters the story. In his 1905 paper, he comes along and proposes what he calls a heuristic point of view, which is really just a fancy way of saying, hey, I've got a hunch, a crazy idea, but let's just see where it goes. And that hunch was about to change everything.
He asks this question that was, it was practically heresy at the time. He asked, what if 100 years of physics has been wrong? What if light isn't a smooth, continuous wave spreading through space at all?
And right here, in his own words from that paper, is the mind-blowing answer. He suggested that the energy in the light wave is made of a finite number of energy quanta, little localized packets that move around without breaking apart and can only be absorbed or created as a single whole unit. Basically, he's saying light is lumpy. It's a staircase, not a ramp.
And these energy quanta, as he called them, were the absolute core of this new idea, discrete, individual packets of energy. It was a complete break from everything physicists believed. We, of course, know them today as photons.
Okay, so this was a totally wild idea, right? But Einstein wasn't just throwing ideas at the wall. He used it to crack another huge mystery that had been stumping physicists for years, the photoelectric effect.
The effect is pretty straightforward. You shine a light on a piece of metal, and sometimes it kicks electrons out. But the mystery was why? According to the old wave theory, a brighter light, a more intense wave, should always have more power to knock out electrons. But that's not what was happening. Not at all. A dim violet light could do it, but a super bright red light did absolutely nothing. Why on earth was that?
Einstein's new theory explained it all, and it's beautifully simple. First, a single packet of light, a quantum, comes in and hits the metal. Then it dumps all of its energy into one single electron, kind of like one billiard ball hitting another. And finally, if that single shot of energy is enough, the electron uses it to break free from the metal. It's a one-on-one deal.
And here's the absolute key. The energy, E, of each little light packet isn't about how bright the light is.
It's determined by its frequency, which is that little Greek letter nu. And frequency is just the scientific way of describing chlor. It's a super simple relationship. The energy of one of these packets is directly tied to its frequency.
And just like that, the whole mystery is solved. Violet light has a much higher frequency than red light. That means each individual quantum of violet light is a little high-energy bullet, powerful enough to knock an electron free. A quantum of red light, on the other hand, is a low-energy packet. It just doesn't have enough punch. You could fire billions of these little red light packets at the metal, but if none of them has enough oomph on its own, nothing happens. It's an all-or-nothing deal.
And the most important part? This wasn't just a neat story he made up. Einstein's theory made very specific, very testable predictions. And when the crucial experiments were finally done years later, the results matched what he had predicted with incredible accuracy. And guess what? He was spot on.
All right, so let's zoom out for a second. What's the final verdict here? What did all of this mean for how we understand light itself?
The case was closed. That huge contradiction that was haunting physics was solved in the weirdest way imaginable. Light wasn't just a wave. It was also a particle. Somehow, it was both at the same time. And this one single idea from just one of the incredible papers he published in his miracle year of 1905, well, it became one of the cornerstones of a brand new science, quantum mechanics.
You see, Einstein hadn't just found a new fact about light. He had pulled back the curtain on this fundamental weirdness at the very heart of reality itself. He gave us the first real look into the quantum world, and it was nothing less than the birth of a new reality.
And all of this leaves us with a question that, honestly, physicists are still wrestling with today. If something as basic as light can be two completely contradictory things at the exact same time, what else about the world we think we know is completely wrong?